There. Prairie View, are you there? Okay, well, it's time to go, so let's pick it up and maybe they'll catch up with us a little bit. We were working a problem when we left last time on Compton. I want to finish that up and then talk a little bit about photon interactions with matter, in particular detectors, and how we detect them. And then we'll move on from this into the next chapter. I'm going to leave Lavoisier's work and the work on the millikanes for you. Lavoisier in particular and other stuff like that is mostly chemistry, where it's covered. There won't be a lot that I will test in that area. And I'll pick up Thomson's work, finding the charge to mass ratio for an electron. The first thing first, let's finish where we were at last time. So when we left last time, we were dealing with a beam of photons directed upon a target. And we got part A, where we calculated the photon coming in by measuring the scattered photons wavelength. And now the question is, what is the maximum kinetic energy that the incident photon can give to the electron? We talked about the fact that the maximum occurs when an electron comes in, a photon comes in, hits the electron, and the photon recoils back at 180 degrees. In other words, it's scattered backwards. That's the most violent type of collision, whether it's a pool ball or what. If you come in and you bounce back, that you're going to give the maximum momentum transfer to the other object. Since momentum and energy are related, you get the maximum kinetic energy. So in this case, we put the cosine of 180, and that got us a -1. We had a 1 minus a -1 made this whole thing 2. And so you find that lambda prime is lambda plus 2 times the Compton wavelength. And that's a universal thing, that's true, okay? Now, to find lambda prime, I've already got 1.49 picometers. And if I remember right, I believe lambda c is 2.43 picometers. So I'll put those two together.
Bless you.
1.49 plus 2 times 2.43. I get 6.35 picometers. Now that's the wavelength. So what I want to do is I want to find the kinetic energy of the electron. So what I need to do is find the energy of the incoming photon, and I need to find the energy of the scattered photon, and the difference between those is what the kinetic energy of the electron gives. Well, I got the wavelength, so I have everything I need to do that. The incoming energy was hc over lambda. That's 1240 keV picometers. Notice that when you work X-ray problems, hc, it's better to work in keV, so you have the picometers there because your wavelengths are in picometers. And you have 1.49 picometers. So if you punch that, 1240, 1.49, you get 832 keV approximately. And then we'll keep one extra decimal. So that was the energy of the incoming photon. The energy of the scattered photon was hc over lambda prime. It was 1240 keV picometers again. This time I'm dividing by 6.35 picometers. If I've done that correctly, I find that it's 195.3 keV. So the kinetic energy of the electron is E minus E prime. So 832.2 keV minus 195.3 keV. About 637 kV. So we got a lot more than the scattered photon. We'll come back to that in a minute because that's actually relevant to the discussion of what's called the backscatter inside our detectors. But it's obviously less than the primary gamma because you can't get more than 100%. All right, so it gets 6/8, 3/4, 75% or so. Simple type of calculation. There are lots of others of this sort. I think I have another one. Came from a different test. I won't go through the whole thing, but show you similar type of problem. In this case, the photon undergoing Compton scattering has an incident energy. So this time they told you the energy coming in. They give you the lambda to the lambda prime. And they told you it scattered at 100, and then they asked you to find the wavelength of the incident photon, which couldn't possibly be right. Okay, so they asked you to find the wavelength, and they gave you the energy. So this was the incident energy. Misread it. Okay. So the first one, they wanted to know the wavelength. P is h over lambda, or lambda is h over p. You can multiply top and bottom by c, you get hc and pc. Pc is the energy, and hc is 1240. You could have gone there directly if you didn't go through here. I went the long way around. Obviously, E is hc over lambda would have been the quick way to do it. All right. So this is certainly the long way around, but hey, work. 1240 kV picometers. You were told it was 210 kV. So it's about 5.9 picometers. In short, be able to use Einstein's relation for photons. It's going to show up a lot, okay? It'll show up back when we do photoelectric problems. It shows up when you do Compton problems. It shows up when we talk about the Bohr atom. No Einstein's energy relation for photons. Not for protons, for photons. It's a little different. And then they ask you to find the wavelength of the scattered photon. Well, now that you got lambda and you have the angle, then you can very quickly find lambda prime. So they could give you the momentum, they could give you the energy, they could give you the wavelength, and then they could ask you to find something else that's Compton scattering. Be able to do all the different types of possibilities they have. Questions about Compton scattering? Usually pretty easy, people score pretty high. Expect to be tested on it. There'll be a Compton problem on the test. Send the book, send the test. There'll be a photoelectric problem, there will be a Compton problem, there will be relativity. You guarantee it. All right? Make sure you can do it. Preview, are y'all there now?
We're here.
All right.
We got disconnected.
Okay. Can you see me?
Yes.
Okay, I can't see. Okay, yeah, right, sure. Okay. I can't see you, but that's okay. As long as you can see me. See the paper. All right. Any questions on Compton that you guys have?
Any questions?
Just tell me we just joined in. We just joined in.
Okay. What I did was finish the problem that I started last class that I didn't finish. We stopped here where the new wavelength, the scattered wavelength, was the incident wavelength that's 2 times the Compton wavelength. That's always going to be true at 180, which is when you're going to give the maximum energy to the electron, and hence have the least energy left to the scattered photon. And then all I did was I calculated the wavelength, and once I knew the wavelength coming in and going out, I calculated their energies by Einstein's relation, and subtracted the 2 energies to find the kinetic. They can give you this information in lots of ways. They can give it to you in wavelengths. They can give you energy, the energy of the photon coming in. They can tell you the momentum of the photon coming in. You need to take that information and convert it to wavelength. Once you know lambda c is constant, you can find lambda prime. They likewise can give you all the information, energy or momentum or lambda for the prime, the scattered. You need to be able to work backwards and find the incident photon that comes in. That's basically the type of problems you have. There will definitely be one on the test. With that, I want to talk a little bit about one other interaction mechanism that's important. So you got photoelectric effect, where you basically come in, photon comes in, photon is swallowed, photon disappears, electron comes out. You have photon comes in, photon scatters, electron comes out, that's Compton. There's even one more bizarre. By the way, I might say the following about this one. What made this important was, this is derived with relativity, and it uses the idea of momentum, that a particle has momentum from Einstein's relativity. So Compton's was a proof of relativity. So that's one of the things that it was historically important, but not so important today. Today we use it for other stuff. The last interaction that we talk about in this section is what's called pair production and annihilation, which again gets back to Einstein's idea that energy and mass are related. So if you have a heavy nucleus, and it's necessary that you have a heavy nucleus, and if a photon is coming in near that nucleus, that photon can convert its energy into a positron and an electron. You must conserve charge. You can't just produce an electron. That wouldn't conserve charge. You have to have an equal positive and an equal negative charge. So a positron and electron. That takes a certain amount of energy. It takes 511 keV of energy to create a positron. It takes 511 keV of energy to create an electron. So unless you have 2 times 511, this process cannot occur. So you put that together and you get that that's a little over 1 MeV. What if you had 3 MeV? Well, the missing energy is given off in kinetic. And they roughly get about usually the same. Not quite, but almost. The reason they don't quite is that this heavy nucleus, which is positively charged, somewhat attracts the electron and somewhat repels the positron. And if you read Iceberg and Resnick in detail, he talks about that. The electron and positron, for instance, could be in your body, that could be in the detector. For all intents and purposes, your body is a detector. The electron will interact by electric forces, slow down, and eventually give up its energy inside a body if it does not come flying out. The positron likely will give up its energy, but it can do something really amazing. When it stops, if it's near matter, it will recombine with one of the electrons inside the material. And at that point, it'll have no kinetic, just its rest mass energy and the rest mass energy of the electron. They recombine, they'll produce 2 photons. Those photons, to conserve momentum, will come out 180 degrees in opposite directions. And they'll each be 511. This is known as annihilation radiation. It's used in PET scans, for instance, as a way to determine cancer. You put something that's a positron emitter and you inject it, and it preferentially gets absorbed in a cancer, and it sends 2 photons out in opposite directions. If you put your detectors on opposite sides, depending on where it comes from in your body, it will hit one of the detectors faster than the other. And you can measure that time difference and determine where on the line the positron was emitted. So, pair production, you turn a photon into mass and antimatter, and annihilation is the inverse. The positron and electron turn themselves back into 2 photons. You notice I said it had to be near a heavy nucleus. With this photon coming in, with its energy and momentum, it is impossible to conserve energy and momentum unless you have a heavy nucleus that can recoil and take an appreciable amount of momentum, but very little energy. You can't do that, it won't work. So this thing requires there to be a lot of heavy nucleuses, or else it won't be very likely. So if you're inside something like water, this is not a likely process. If you're in something that's got like bismuth, this is a much more likely process. So one of the things people want to do with detectors is often to have heavy elements inside the detector. That's why they have things like sodium iodide, bismuth, germanium oxide for detectors. Now, there's a lot of weird things that happen inside of detectors. If you're trying to detect these in lab, which we will. And that's because all of these processes can be happening. So, most detectors are made of some sort of crystal. That crystal's often sodium iodide because it's cheapest. But it could be other materials that scintillate. And this photon will come in, and that photon may undergo photoelectric effect and knock off electron. In which case, that electron will get stopped in the crystal, and you'll detect all the energy. So if this energy is 4 MeV, you'll catch 4 MeV of energy. And in your spectra, you'd see a peak at 4 MeV. But there are other things that can happen.
Is it photoelectric effect not very common at that high energy?
That's correct. It would not be very high. It would not be very common at that high in energy. He says, isn't it true it's not that high at that common at that energy? And I would agree with you. It's much more likely to happen around 10 MeV. I'm sorry, 10 keV than it is up at the MeV. It's also possible that this gamma could come in and scatter out like this. And here's the thing. This gamma prime is lost. You're going to lose its energy. What you're going to catch is the electron. So you're going to get electrons of different energies depending on which angle of Compton scattering you have. The only thing you can really tell me is the maximum energy, because that's when this photon comes in and scatters 180 degrees. That point has a name. It's called the Compton edge. And it's the answer to the question we just got through working. What's the maximum kinetic energy an electron can have? At any other angle, it'll come in at some other value. And so you'll get a continuous distribution for different angles. This one's for 180 scattering. These are at some other angle. The electron didn't get as much. If the energy is high enough, then you're going to get pair production. And if you get pair production, positron-electron, and if that positron-electron recombine, it's possible the photon could get out, and you'll lose one 511, in which case you'll get a peak. This will be at 4 MeV minus 0.511. And the name for that peak is called the first escape peak, and it's because there was one escaping 511 gamma. It's also possible that the second one might get out. If that happens, you're going to lose 2 times 511, and you get another peak, called the second escape. This all came from a spectra that really only had one energy of gamma. These artifacts are due to these interactions and the fact that what you detect is the energy deposited in the crystal, and not necessarily all the energy. This peak here is called the photopeak, but it's really a bad name because, as Keaton said, it's not likely to have been a photoelectric interaction. What it really is likely to have been is it did Compton scattering, and the scattered photon got caught, and the electron got caught, so you got all the energy, just as if it had been a photoelectric interaction. And so you put it in this channel. Same thing with this. If it comes in and creates positron-electron, and you catch all the gammas, it'll still end up over here. So you really don't know what interaction occurred. You just know you caught all the energy. This one, you lost a photon. This one, you lost 2 photons. And these, you lost scattered photons. Now, if that's not bad enough, it can get even worse. If you've shielded your detector, your Comanche Peak over here, so you put lead or something on it, you can get a couple of other artifacts. You can have one of these gammas come in and, let's say, like this. Maybe there's something back here. They can go like that, scatter, and go back in the detector. So in this case, they went up here, they scattered, so they got the 180 value, and it comes back, and it creates another peak back down here. That's called the backscatter peak. It's not a new element, it's not new radioactivity, it just happens to be there because it bounced off an electron. We used to use this in the honors class as a way to measure the rest mass energy of electrons. All you need is algebra. And last but not least, if there's lead or something around here, it might hit the lead, knock some electrons off the lead create characteristic X-rays, and those X-rays will put additional peaks on this spectrum. So you can see that measuring gammas is not a trivial thing. One has to think about all the different ways that it can interact with your detector and with the surroundings about it. And it's an important thing because we might want to know the radiation that's coming to you if you work at a nuclear power plant. We might want to be able to put radiation in you if you're in a medical facility. And of course, all of this was important for us to understand the nucleus in order to understand modern physics. So understanding these detectors is kind of important. With that being said, I have a video, very short. Let me see if I can.
Gamma rays are detected by the sodium iodide crystal. The student coats the crystal with silicone grease, makes a good optical contact with the face of the photomultiplier tube. Now he covers the whole assembly with a steel shield. We will display the spectrum of manganese 56. In the range we are observing, there is only one gamma ray of energy 0.85 MeV. The first pattern is ragged because only a few counts have been recorded. Statistical fluctuations are less noticeable when more counts have been recorded. Finally, with still more counts available, the curve is quite smooth. It shows some interesting features. The photo peak at 0.85 MeV gives the energy of the gamma ray photons. The Compton edge is at about 0.6 MeV, and the backscatter peak is at about 0.2 MeV. These last two features are secondary effects caused by the scattering of gamma rays by the electrons in the crystal and in the shield.
One other thing that I wanted to, if I can get back, is in the next chapter, we're going to deal with, I think I went too far. We're going to deal with line spectrum. Of course, we have a spectrometer. You'll have to be doing a lab on it as well. So one of the big questions in the next chapter is to look at the fact
crystals of sodium chloride on a Meeker burner give a
is the fact that the absorption spectrum, that is, when you shine light through a burning gas, is exactly the same as a heated gas emission spectrum. And this was a fundamental idea that Niels Bohr needed to develop his model in the next section. And so, while I have an emission spectrum, I don't actually have an absorption spectrum right here. So I thought I'd show you one that shows this effect. Oops, sorry, wrong.
Crystals of sodium chloride on a meeker burner give a yellow flame which contains sodium vapor. Here's the spectrum of sodium, 2 yellow lines of almost the same wavelength. This is the emission spectrum. Now we shine white light through the vapor and see the absorption spectrum of sodium. 2 dark lines at the same 2 wavelengths which are characteristic of the element sodium. Here's the comparison. Emission at the bottom, absorption at the top. Absorption by a liquid gives bands rather than sharp lines. Hemoglobin from a vein gives a fairly broad band in the green region of the spectrum. By bubbling air through a hemoglobin solution, we get oxyhemoglobin, as from an artery. The spectrum is quite different. The difference is caused by adding just 4 atoms of oxygen to a molecule that already has over 9,000 atoms. Finally, to illustrate absorption by a solid, here's a fairly complicated absorption spectrum of a type of glass which contains several of the rare earths.
So absorption spectroscopy, or emission spectroscopy, turns out to be an incredibly powerful technique. You can use it to determine materials, you can use it to determine their compounding and how they're connecting. And so chemists use it a lot. To be able to explain that, people knew absorption and emission spectrum back in the late 1800s. They had measured all the lines. You could have filled up a room this size with all the data. Niels Bohr, with 4 assumptions and nothing else, is able to explain everything. And he does it by a very bizarre set of assumptions. But it's the beginning, really, of power of quantum mechanics, that if you understand these things, you can take it and use it and apply it to solve all sorts of things by understanding how the atoms actually work. All right, finishing up the last bit of stuff that we have, I think was to talk about photons going through matter in the book, and that dealt with the question of, let's say you had a set of photons, and we're not so interested in their energy, but we're interested in how many of them get to a material of different thickness. So you have some material, and for the moment, I'm going to make 2 assumptions like the book does. He doesn't say that, but he does. And his assumptions are as follows. 1, he's going to assume that the material that he's messing with is of a uniform material. It only has one basic type of atoms. And number 2, he's going to assume that the photons coming in are monoenergetic. Not true if it came, for instance, from our X-ray machine. So he's going to assume that these guys are all just one type of photon in terms of energy. And there's only one type of atom set inside that material. And he wants to know, for a given material, basically how many of these gets through this. Now, instead of counting photons, we usually talk about intensity. That is power per area. So the intensity change, di dx, as you change the thickness, where this is dx, depends on a couple of things. Well, first of all, it's going to go down. It's not going to go up. And it's going to go down because some of these photons are going to be scattered out of the beam. And so they don't get to this side. It's going to depend on the probability of a photon interacting with an atom. There's a name for that in physics. It's called the cross-section. There's more discussion later in your book on the chapter that deals with neutrons and nuclear physics. So that's the probability, for instance, kind of like a batter. That's a probability that if the photon was to go through and there was only one atom in the material, that's the probability it would interact, and it would get scattered out. Now, it could be interacted by photoelectric, it could interact by Compton, it could interact by pair production. So in reality, this sigma depends on the probability of the pair, the probability of Compton, and the probability of photoelectric. And those probabilities are extremely energy dependent. So at low energies, this might dominate. At middle energies, that might dominate. And at high energies, this might dominate. But you have to add up all three probabilities because any one of them prevents the photon from going through. But that's if there's only one atom. There's not one atom. There are a bunch of atoms in here. So we need to determine how to account for that, and that's by the density of atoms. For most materials, we don't use a meter of material, we use a centimeter of material. So it's usually in atoms per cubic centimeter is what's done, not in atoms per meter cubed. So that's the probability that a single photon interacts with a single atom. When you multiply by that, that's the probability a single photon interacts with all of these atoms. And one more, there's more than one photon. So you need to account for the intensity of the light. Now, these two things, assuming that you have a monoenergetic material, are constants. And if they're constants, you can multiply those two constants together and make a new constant. And that's what's usually done. Just take this, and they take that, the cross-section and the atomic density, they multiply them together, and they give it a name. Called the linear attenuation coefficient in the book. And it's only a constant if these two things are constant. So if you mix around, if half the material's made of iron and the next half's made of something else, well, it's not constant. If this has different energies and this probability is energy dependent, as you go through the material, the easier to stop photons will get stopped, and only the hard ones will get through. And this number will change. All the stuff in the book assumes the simplest case. It assumes these two stay constant. If we do that, we get the following equation the book gets. That equation. And that's an easy differential equation to solve. It's separable, so we can bring the I under dI. And mu dx, and we can integrate that from the initial intensity to the final, and from the initial x to the final x. The integral di over I is the natural log. So that becomes the natural log of the intensity over the initial intensity. And because we said this is a constant, This is going to come outside, and we just have the integral dx, which is x. Get rid of the natural log, we take the exponential of both sides. And solve for I gives us this equation that's in the book. Now, what this says that if you shine photons, I don't care what photons they are, X-rays, gamma rays, light rays, whatever, on a material of a certain thickness, as the thickness gets thicker, the number that goes through exponentially goes down. This has a lot of important applications. It has importance in shielding for nuclear reactors. It has importance in cancer therapy and the application of modern physics to medicine. It has importance in the way you build detectors. It has lots of applications. So, example, you might want to decay or decrease something by a certain amount. That is, you want I to be a tenth of what the initial intensity was. So what thickness is required to reduce intensity by 90%? But shielding with mu equal, I don't know, 0.5 centimeters to the minus 1 is used. So you've got some set of gammas coming at you, and you want to cut them down because it may be bad for you, and so your boss comes in and he says, hey, look, I want you to reduce my flux by 90% to make it safe, and this is the material that you have. Where would I get this number? I look it up in the data table. They're all over on the web. On a test, you'll be given it, obviously, but on the real world, you look it up on the web. And that's what you're going to use. All right, well, what you know is I over I naught is 0.1. And that's equal to e to the minus mu x. So the natural log of 0.1 is equal to minus mu x. The natural log of 0.1 is minus the natural log of 10. So we can get rid of the minus signs. So x is the natural log of 10 over 0.5 centimeters to the minus 1. You need 4.61 centimeters of material. That's how thick the shield needs to be. Those type of calculations are pretty simple. There's more to this section I will not plan to go into. Mu is often given in terms of mass density rather than, so it's in kilograms per meter. I'll leave that for class if you decide to go into that particular specialty. The one other thing I do want to talk about is this has ramifications in medicine for the following. Let's say that here's you. Here's a tumor. Here's your spinal column, which we would like not to radiate and kill, because if we do, we're going to paralyze you. And we've decided that we're going to kill these cells by shooting photons at them. Like this. My problem. The intensity, and hence the death of the cell, looks like this. it exponentially decreases. From some I not. So if I'm at this depth, whatever that x is, let's say it's over here, that's the only amount of photons that the cancer cell is getting. Your healthy cells here are getting a much bigger dose. And I'm killing them and making you sick. Now, what I can do, and what is done, is that I can spin and shoot these photons in from different directions. I'll make these sick too, but what I can do is I can sum up in this area. And that's what's done in a thing called IMXLT. It's a standard method by which people, if you're not going to MD Anderson, use to kill cancer. There's still a bad thing. Besides the fact I'm doing a lot of making you sick, even if only mildly, by dosing all these cells, I've also got another problem. No matter what I do, these photons will continue through and also hit that spinal cord. You will always have things dosed behind the object, and there's nothing you can do about that if you use photons. So you have the potential to create secondary tumors, especially if it's a young person. You have the possibility of creating very bad side effects such as paralysis, and you can't do anything if you use photons, which is the standard method. If you use protons, it turns out the distribution is much different. It looks like this. More like that. Nothing can go beyond the maximum energy of a proton. So if I make sure the proton runs out of energy in the tumor, there's absolutely no way it will do any damage to anything behind it. This is one of the reasons proton therapy is a big thing. Much harder to do, requires a much bigger accelerator, requires much more physicists who are capable, makes electrical engineers and computer scientists to run this. Much harder to do, but it's got tremendously improved ability in terms of fighting tumors because you don't have the exponential function. And you can't get away. Photons work off the exponential function. That's the way they do. They either work or they don't work. They have photons. Yeah.
So if you have a tumor in your brain and they can't get into it, they use this stuff?
They can use either one. Right now, if you go to Dallas, you're going to get photons because it's the only game in town. If you go to MD Anderson, you're going to get proton therapy.
So proton's probably better.
Yes, it is, but it's much more expensive.
That's good to check.
By the way, Dallas is building a proton therapy. There are more than 20 new proton therapies going into build right now. And they're going to need, hundreds and hundreds of trained physicists capable of being able to handle these machines. You don't have the trained people, you can't, doesn't matter how fancy the machine is, it's worthless without people who know and understand the science behind it.
So they built an actual accelerator in this building?
Oh yes, the accelerator would be about the size of this building here, with different gantries for each room. So you have this gigantic, you get this giant building. You have this big, gigantic accelerator, and then you'll actually have it come out with beam lines into different rooms. So you can bend it there, you can bend it in the next room. So you can start putting patients room after room after room.
Wow. This is better than humans, I guess.
You got to get maximum throughput, get your money back. It costs a lot of money to build these things. You cost $1 billion. You got to make sure you treat a lot of people and get your money.
As long as insurance covers.
That's the financial side that I don't really care so much about. I care about building stuff. But it's important. If you ain't got the money, you don't build anything. So there's jobs in that area if you'd like that area. But all of that requires you to understand modern physics. All right, moving on to the next thing. I'm going to leave you the problem that dealt with the detectors concerning this particular reaction that we use for the Army to do a lot of research. So you're asked to find the photopeak, escape peaks, and the Compton edge, and I'll leave that for you. Again, that'd be a good question to put on an exam. J.J. Thompson. J.J. was an interesting guy. He was a very large man. He had big hands. And in the time when he was doing it, things were made of glass. And the problem with glass is you need to be gentle. J.J. was not. So, quote his son, T.P., "It was always best never to let J.J. touch anything." And when he did this experiment, in fact, his son helped. And JJ proves with this experiment that electron is a particle. And GP comes back and proves it's a wave. And they both won the Nobel Prize.
The same Nobel Prize or
Huh?
different Nobel Prize?
Different Nobel Prizes. So they're one of only two father-sons to win the Nobel Prize. The other one is Neil and Age Bohr. Neil put electrons going in orbit around the nucleus, and Age put protons and neutrons inside the nucleus going around. So here's the thing. JJ was not the first to do this experiment. It involves taking a glass tube, putting a battery to accelerate a set of electrons, putting some sort of circuitry here to create thermionic emission. So he's got a heater here I didn't show. He heats the electrons, gets the electrons free, puts a voltage here, accelerates the electrons out, shoots them out, and puts a couple of plates. And he uses those plates to deflect the electrons. Other people have done this. Yeah.
Was Hall the first one to do that
No.
experiment?
No, Hall's much later. He saw it second. Other people have done this. The problem is they didn't get the tube a really good vacuum. And if you don't, and it has dirt or anything inside it, what happens is it charges up. And it produces its own field that cancels the field of the plates. So sometimes it appeared that they got deflected, and so they must be charged particles. And sometimes they didn't, in which case people thought that they were photons, because they didn't know about photons, but they thought they were light. What Thomson did is, A, he got the vacuum very well. Got a good vacuum, okay? And second, in addition to this, he also put a magnetic field perpendicular to it that could cancel the electric field. Those two things makes this experiment really unique. Now, this is a really good example of learning and making sure you know physics 1 and 2. Because almost everything in this is physics 1 and 2. First, let's assume that he doesn't have the magnetic field on. He only has the plates. He has a charged particle coming through here. It has a certain energy, so it's flying around with some V. We call that Vx. It gets in this plate. This plate applies an electric field and its force vertically, not horizontally, so there's no acceleration this way. The only force is up. So you draw a free body diagram. Free body diagram says that the sum of the forces in y divided by the mass is acceleration. And the force is Q times the electric field. That's not energy, that's electric field. So just physics 2 and physics 1. Next problem that you have to be careful about. Well, if I look at this, I see a charge that turns out to be a constant, a mass that turns out to be a constant, and an electric field, if I build a parallel plate, that's constant. So therefore, the acceleration is constant. And I can use what type of equations to work constant acceleration problems? Kinematics. I love kinematic equations. So if I'm doing kinematics, I have Vy is equal to the initial velocity in the y direction plus the acceleration in y times time. And initially, I lined it up so that the beam was going parallel to the x-axis. Now I'm going to have to find time. And this thing goes whoop, and I can't see them individually, so it's not like I can put a stopwatch on them. So I have to find a way to trick myself to find time. Well, let's see. In the x direction, kinematics also works. The velocity in x times the time has to be the distance that you travel. So you can solve that for t. That's the length of the plates divided by the velocity along the x direction. So now what I want to do, I want to take this and I want to plug it in for t. I want to take that and I want to plug it in for a. So if I do that, let's see, I've got a, which is q e over m And then I have times T, which is L, times Vx. The length of the plates, that's not too hard to find. I can do that. Vx, that's going to be a problem. How the heck am I going to get the speed? I'll show you in a minute. I got a way to do that. Botched something up. Oh, I know what I did. Sorry about that. What I did wrong is that this is Vy, and now I need to finish it. Convert that. So Q over M is equal to Vy, Vx, M over EL. All right. Skipped a line. Sorry about that.
And you sure the M should be there?
Should the M
Just not,
get it right now?
Yeah.
All right. So I skipped a line. I find the Vy and then I rearrange it to Q over M. So Q over M is Vx, Vy, E over L. My problem, this is the final speed at which it leaves going vertically upward. How am I going to measure that? This is the horizontal speed. How am I going to measure that? This is the length of the plate. Well, I can use a ruler. I got that one down. This is the electric field. It turns out that's not too hard either because we did parallel plate capacitors back in Physics 2. And you may remember that if you do a parallel plate capacitor, the voltage is equal to the electric field times the distance between the plates. This is force times distance. So I can do that. If I know the voltage and I know the gap between the plates, I can find the electric field. So at least I got that one done. I'll go ahead and put that in here. Vx, Vy. On the bottom, I'm going to get V. On the top, I'm going to get a D, and then I get an L. All right. So, gap of the plate, length of the plate, voltage on the plates, but these two are a problem. How am I going to get rid of those? Thomson was an ingenious guy. He had two things he knew. One, he knew about a beam filter, which he's going to use to find Vx, and the second one that he knew was that he knew he could get rid of Vy in terms of Vx. How do you know that? He said, look, if I build this tube really long, let's see if I have a picture of, I don't know if I have a picture of this tube here. That plate is very small compared to that length. Then it turns out that I'm only going to give it a very small push. It's going to do most of its deflection after it leaves this plate. So I know it follows a curved path, and then it follows a straight line after it leaves the force. Let's ignore the little curve. And let's just say that it leaves right here and goes in a straight line. If I do that, then if that's Vx, that's Vy, that's theta, then the tan of theta is Vy over Vx. And I think we're done, aren't we, for time? All right, so we'll stop here.